I'm in the process of trying to repair and restore this PDP11-34A vintage computer. It's turning into a bit of a nightmare to get going. It's developing fault after fault, and the faults are currently developing more quickly than I'm repairing them. So in the previous video I got as far as trying to boot from floppy drive. You can see I now have the drive taken out of the way. And I started shooting a video to show the next step in trying to get it to boot. I could actually read the floppy drive using PDP GUI, and it turned out that the floppy disk I had had a corrupt block, and that's why it wasn't booting. So you could see going part way through the boot process. But unfortunately, as I was shooting that video, yet another fault developed, and now it won't read the disk at all. Starting the process, but then the PDP hangs with a bus error, so I suspect it's getting stuck partway through a bus cycle, or there's a fault with the interface card. But it is also possible there's a fault with the backplane or the CPU or the memory card, the drive itself, or the interface. And so I need to look at this in more detail, and I was originally going to make this video about trying to get that fault resolved. But I've been using a memory card in this system that I don't have any technical information for, and because the interface for the floppy drive uses DMA, it talks directly to memory and doesn't go through the CPU. So really I need to start looking at the memory in a bit more detail. It's even possible it's a fault with the memory card itself. Now, I do know this memory card has some faults. I do eventually want to use this because it's quite a nice memory card, but as I say, I don't have any technical information for it, so I've got no idea what these switches are for. Luckily, I do now have a proper PDP flip chip memory card, and haven't really looked at this yet. I did plug it in when I received it, but unfortunately it's got a fault and the PDP won't boot with this plugged in. And so what we're going to do in this video is try and repair this card, try and get this working. If you're interested, this is an M7847. It's in fairly good physical condition. It doesn't look to be badly damaged, but it just doesn't allow the PDP to boot. So what I'm going to do is get this set up in some risers on the PDP. Would be easier if I'd done this when I didn't have the other cards in. I could remove the other cards, but I want to just plug this in to risers and see what it does. So I'll get this plugged in and we'll see if we can figure out why it doesn't work. Okay, so I've plugged this in. I haven't looked at it yet, so I haven't powered this up, other than when I originally plugged it in and the PDP didn't boot up, so I removed it. And I thought we'd go through this together and try and figure out what's going on. So we'll start by powering this up. I did check, incidentally, usual static checks, looking for shorts and that sort of thing, and it all seems fine. So we'll power this up. It does say it's running, but nothing appears on the terminal, so we'll try and halt, and we're getting a bus error. So there's obviously something wrong, so we need to try and force this to halt. Okay, so it's now halted. And what we can do now is try writing direct to memory and see if we can read and write memory in the proper way. So we'll start with address 0. Value of 0, we'll deposit that, and then we'll examine, and that looks fine. Okay, and now we'll go up to address 1000. Deposit a value of 0, try and examine that, and it appears we've got a stuck bit, so we'll just try that again. So we'll go back to address 0, start at address 0, deposit a value of 0, check the address is 0, examine, and that looks fine. We'll try putting all 1s in that address, deposit that, read that back, and that looks fine. We'll try setting it back to 0. So it looks like we're okay at address 0, so we'll go up to 1000 again. This is octal, of course. Try putting 0 back in, check the address is still 1000. and again we've got a stuck bit, so we'll try putting all ones into that address and see if it's just the one bit or if they're all stuck. So we can set them all to 1, and we'll try putting 0 into that address. Read it back, and we can see that bit 10 is stuck, so we'll go higher still. We'll go now up to address 4000. Try and put a 1, read that back, and the bit is still stuck. We'll go up to 7000. Read that back, still stuck. So we'll go up to the next address. Examine that, and it looks like we can once again successfully write data. Let's try setting everything to a 1. Read it back. Try setting it to a 0. That back, and it's gone back to not successfully writing the bit values. Okay, so we'll go back to address 0, deposit a 0, examine that, that looks fine. So it looks like we've got an issue with the memory, and one of the bits is sticking at certain addresses. These cards are actually fairly easy to deal with. I've repaired probably 25 of these over the last 10 or 15 years, and it's nearly always the same thing. It's usually a failed DRAM chip. These are DRAM boards, of course, and they look quite complex when you first look at them, but they're actually not. If you're not familiar with DRAMs, what makes the overall operation more complex is that the D in DRAM stands for dynamic, and really they're just a collection of small capacitors and with some gates and sensors, and when you store data, you just store the data in a charged capacitor. It's a very small capacitor, there's thousands on each chip, and within a few tens of milliseconds that capacitor will discharge and you lose the data. So the memory is retained by constantly refreshing it, and there are two control lines that go into DRAM chips: column address strobe, row address strobe, and by toggling one of those you normally refresh the memory. It just causes it to rewrite the data it's got in. And the complication there is you can't do that at the same time as you are effectively reading the memory, at least not with single port RAM. And so there is electronics in here to kind of arbitrate who's allowed to access the memory at any one time. So if there's a refresh cycle going on, then the user access is temporarily put on hold. It's only for a few microseconds, but it does need to be taken care of by the electronics. In this system, 16K memory card, it uses 4K by 1-bit memory chips. So there are 4 banks, and that's what this arrangement here is. It just selects one of the banks in turn, and or based on the memory address that's supplied. And then there is some electronics to deal with the RAS and CAS timing, and ultimately all this is used to decode a memory address. Now these chips are 4096 chips, and if you look at the spec for them, it looks a bit odd saying that they're 4K chips, because that kind of implies you need 12 address bits. And it does have 12 address bits, but they're all entered through 6 common pins. It's done in 2 6-bit chunks. One 6-bit chunk of the address is clocked in when the CAS signal goes low, and the second group of 6 bits when the RAS signal goes low. So it does it in 2 chunks. So there is memory decoding for the high and low 6 bits, which again makes it look more complex. But this actually makes it a bit easier for us, because we can kind of see, based on what the card is doing, what's going on. And then we have the bank select gates, and we can kind of tell that the memory overall is kind of doing what we expect it to. We've got, of course, the bus drivers, and this is what connects the card to the unibus. I suspect this is working fine, because otherwise we'd get issues at all addresses. So if it was one bit that was stuck, for example, we get the same issue throughout the entire memory space, but we're not. We then get on to the memory array itself, and this gives us the most clues that the chips are arranged in banks of 4. So each of this column of chips is 1 bit of the overall memory space. Notice that all the inputs are common and all the outputs are common. This is kind of why you get this odd semi-erratic behavior, because if one of these starts to fail, it can affect the output from the other 3. But what we can do is narrow it down and try to figure out which particular one is causing a problem. And the easiest way of doing this, especially with 1-bit devices, you can use a logic analyzer if you've got one. It's just figure out which bit is causing a problem, and obviously there's quite a few of these. There's quite a few pages of the array, but they're all just duplications. It's just, as I say, 1 column of 4 chips per bit. And all we need to do is look at the input when we put certain values in, look at the output, and then we can use a scope to determine if this is working or not, and then hopefully narrow down which particular chip is causing the problem, or chips. So we know it's bit 10, so we'll find bit 10 on the schematic. These are labelled. You want me to read this? In fact, I can't really read it properly here. It's these are handwritten, and some of the writing is not particularly clear. But we'll find the bit 10 column, and then we'll check the 4 devices in that particular column. Unfortunately, the fault turned out to be a lot more straightforward to solve than I'd expected, so apologies, it's going to be a fairly boring video. It's now working, and a very similar problem to what I had with the bootloader card, in that this board at one point seems like it's been stacked with some other boards, and one of the traces had been gouged, and it's one of the traces in the address decoder. Very simple address decoder in this. It just breaks the address into 2 chunks, and it uses that for the RAS and the CAS setup for the address internally with the DRAM chips. And we were only getting half the address coming through. One of the 2 parts of the decoder wasn't working, and the upshot of that, it was effectively, whatever you set the switches to, it was mapping the RAM into the upper portion of the memory space, or at least it was splitting it, so part was in the lower part of the memory and space, and part was in the upper. And so the bit value we were seeing was actually one of the other system registers, and they were conflicting. It doesn't do any harm, of course, because of the nature of the unibus. It just stops it working properly. So what I did when I realized that the memory chips didn't seem to be being triggered, so what I was doing was using the scope to look at the CAS and the RAS input signals, and they were never, they're constantly toggling because it's going through refresh cycles, but you can normally tell, if you put a scope on there, you can tell when you write to a particular chip, you'll see a very brief change in the scope. The repetitive nature of the refresh signal will briefly change, and you'll see which particular device you're writing to, but it was never writing to half of the chips on the RAM board, so there was something weird going on. So what I ended up doing, you could do this with a scope. You only need really 4 channels. You can get away with 2. Let's look at the CAS and the RAS signals. It's better if you can look at the CAS, RAS, chip enable and the write enable signals and use those to trigger your scope, and then you can look at the data in, data out and see if it matches what you'd expect. Of course, with a logic analyzer it's far easier to do that. So just to give a bit of interest to this video, I've hooked up the logic analyzer, and we'll have a look at the signals that you can pick up on these DRAM chips and use that to determine if a particular chip is faulty. It's very similar to what we looked at when we were examining the devices on the CPU board, but this is just far more repetitive. It's all the same thing. If you can narrow it down to a particular bit, then all well and good, and I'm actually looking at bit 10 here. Again, bear in mind with these boards there are 2 extra bits that are used for parity, so there are actually 18 chips per bank, and make sure you don't hook up the analyzer to those, because unless you have the parity unit plugged in, they're not going to do anything. So I'll just move the camera and we'll have a look at the logic analyzer and see what signals we should expect to see from these DRAM chips. So I've got the logic analyzer set up. We've got 6 bits for the address, data in, data out, write enable, CAS, RAS and chip select. And on the trigger side we've got a trigger setting for when all 4 control signals go low. So that is when this particular chip is effectively being addressed, either written, in this case written to. If you want to look at when it's just been read from, then obviously you just ignore the write enable line. Go to waveform on the analyzer, and I'll now try writing to address 0, which is the bank that we've, that's an address in the bank that we have the analyzer clipped to. I'll try depositing a value, and in this case I'm writing a value of 0. So you can see that the address will be 77, all bits set, because we are effectively selecting a 0 address and the bits are inverted. And we've got data in value of 0, which we should. I'm writing a value of 0. This is only 1 bit, don't forget. Data out, when we clock the bit with the write enable, and we have CAS. In fact, we'll get RAS on here as well. Okay, so we've now got all 4 control lines showing, and as you can see, when all 4 go low, we trigger the analyzer. And in this case, when this memory device was accessed, the 0 on the input, not only was it latched, we hope, into the device, but it came out of the output. What we can now do is go through and check that it has been successfully written. So we'll change the write enable to don't care. In fact, what we'll do is we'll set it to a 1 to make absolutely certain that we only capture the read. Go back, and this time we'll try reading from the same address. And so notice the write enable had stayed high. The data in doesn't really matter, but in this case notice that the data out drops to 0, so we are successfully reading back the 0 that we put in. We'll try now writing to the device. In this case we want to reset write enable trigger to 0. Rearm, and I'm going to try writing a value of, or at least all 1s, to that memory location. And this time notice that the data in goes high, and it does this before the CAS falling edge is the kind of trigger point for this particular board in terms of when it writes the data. So we have data in going high, data out, it kind of stays high, it's high to start with, and then the control signals all drop. We can now hopefully read that back, so we'll reset write enable to 1, rearm the analyzer, and this time I'm just going to read that address. Okay, so what we're looking at here is we can ignore data in, and it's the data out at the falling edge of the CAS signal we're interested in, and notice it goes high, so we are successfully reading back a 1. So that's how you can test these chips one at a time. It saves you desoldering them, and because they are all wired together, at least in banks of 4, with the common data in, common data out, it can make it a bit tricky just trying to do static testing with a scope. You can do it with multiple channels, but obviously with a logic analyzer you can pinpoint the exact device that was faulty. Unfortunately in this case we didn't have any faulty devices, it was just a bit of gouging on the board, and I just put a small solder bridge wire on there, and then it started behaving correctly. So I'll just move the camera. So looking back at the console, we should now be able to boot up, and we can. Not only that, but we can halt it, we don't get the bus error anymore, and I can confirm that the terminal is showing us the normal boot up. So that's solved the problem with the RAM board. A bit more straightforward than I was expecting. So not a particularly interesting video, but I thought I would include it just to be complete, and you could see what other things I needed to do to get this machine working. So I can now fit that board to the backplane, and in the next video I'll get back on to try and fault find on the actual floppy drive.